evening and welcome live to Television Centre. Now in just a moment I'll be demonstrating this new device that makes it possible to locate me anywhere in the building.
And I'll be looking at a device that'll help me to locate myself underwater. We'll also have the latest pictures from the Soviet space mission as its spacecraft closes in on the Martian moon Phobos, and how archaeologists are finding new ways of looking at old sites. But first, back to Judith.
For anyone working in a large building, say a security guard or a nurse, you can feel pretty vulnerable. But with this, you can call up help by just pressing one button. And then this identifies precisely where and who you are.
Uh-oh, someone's in trouble, because that bleep shows up on the diagram and floor plan here. And down here we can see it says Judith on the ground floor. Well, this control centre's at the end of a series of radio link devices which relay the panic button signal. And receivers like this one are fitted at various points around the building. Every 4 seconds, they're interrogated, again by radio, by the computer. And when a panic button goes off, it sends out a coded radio signal which is picked up by only the receivers within range. These receivers send coded radio signals to the computer saying they've heard the alarm. The computer then selects the closest 4, and since the computer knows the distances between the receivers, it can work out from the timings of their signals the location of the panic button to an accuracy of 3 feet. Looks like there's somebody else in need. It's on the 4th floor, according to the diagrams, and I believe it's Maggie.
That's right, Howard. In fact, I'm standing right underneath one of those receivers you were talking about. And the only crucial thing about them is that they must be positioned correctly because you don't want any steel to get in the way of the radio waves. Now, the system is fairly versatile because, as well as acting as a personal alarm, it can also double as an anti-theft device. Because say you've got a touring exhibition or you've been lent something of immense value, like this, the winning Oni's trophy for the Grand National. What you'd do then is to pop the button underneath it so that if anyone actually moved it, the alarm would sound.
Yes, and there goes the alarm, and the security guard gets an immediate warning about that. Let's reset it. Oh, and immediately, it's all go here. There's someone now. Let me just do that again. Yes, I thought it was another different one. As you can see, it's now in the basement. Judith.
Yes, it's me. And I'm here, run VT please, to hand over to a report from Peter.
Diving can be a dangerous business, so it's important to know what's below the surface. Now, this little gadget can tell me my depth down to 75 metres. I don't plan to be going that deep today. It's an echo sounder that sends a high-frequency sound signal down to the bottom and picks up the reflection, 12.7 metres. Well, that should be enough. It works on exactly the same principle as an ordinary echo sounder, but normally they're only found on larger boats connected up to complex electrical equipment. But this is totally independent. It runs on batteries, and it's completely sealed, so it can be used by divers to detect underwater obstacles. But for those of us with more peaceful pursuits in mind, finding an area of deeper water can mean a bigger catch. The echo sounder can even detect more elusive objects like shoals of fish. Because a sudden change in depth means that there's something moving under the surface.
On April the 9th, a Soviet spacecraft, which for the last month has been in orbit around Mars, will attempt a breathtaking series of experiments. In the most complex interplanetary mission since Voyager's journey to the outer planets, the unmanned spacecraft will swoop within 30 metres of the surface of the Martian moon Phobos, it'll fire lasers at it and jettison 2 landing craft. Well, already the spacecraft has sent back these impressive pictures. Now, Phobos is a mere 27 kilometres long with minimal gravity and therefore no atmosphere. Geologists and astronomers are particularly interested in Phobos because, unlike the planets, they believe it has changed very little since the formation of the solar system. The mission began in July 1988 with the launch of Phobos 1, followed by Phobos 2 a week later. In August, disaster struck. A single-digit software error caused Phobos 1 to point its solar cells away from the Sun, depriving it of all power. Fortunately, Phobos 2 survived the 190 million kilometre journey, completing it in 7 months. At the end of January, it approached Phobos and Mars, initially going in an elliptical orbit, passing within 500 kilometres of the surface of the red planet. These are the pictures of Mars the spacecraft sent back to Earth, and they identified canyons and volcanic craters. Then the spacecraft began the painstaking task of closing in on Phobos itself. A second ellipse brought it much closer, giving really precise information on Phobos's orbit. Finally, Mission Control put the spacecraft in a circular orbit of almost exactly the same radius and speed of rotation as Phobos itself. The pictures coming back from Phobos have allowed them to gradually get closer in. It's taken a month of reducing this orbit for the Soviets to find the ideal location for the climax to the mission, the close encounter. On April the 9th, the spacecraft will descend from its present orbit for a swoop over the surface of Phobos at a height of just 30 metres. At a speed of about 20 kilometres per hour, it'll traverse the surface in under half an hour. Now, this in itself is quite an astounding task. The spacecraft will have to control its own height and negotiate any rough terrain it may encounter unaided. At this distance from Earth, it takes a full 12 minutes for a radio instruction to arrive from Moscow. As it travels along, and provided it doesn't crash, the onboard cameras will beam back what everyone hopes will be uniquely detailed pictures of the surface. At the same time, a high-powered laser will fire at a point a millimetre square on the ground 30 metres below. If any of the resulting vapour can be captured back on the spacecraft, it'll be analysed by a mass spectrometer to reveal its elements. It's also equipped with an ion gun that will attempt to dislodge and capture charged atoms of the surface material. In the remaining few minutes of the half-hour encounter, Phobos 2 will jettison its landers. Now, Harpoon will anchor itself onto the surface and send back very precise information on fluctuations in gravity over the next 12 months. Grasshopper, on the other hand, will function for just 4 hours. Taking advantage of the extremely low gravity, this spring-loaded foot will enable the lander to make 40-metre hops. And at each landing point, it'll test a sample of the soil and then hop on. At the end of this close encounter, the spacecraft will climb to prevent it crashing into Phobos on the next orbit. Well, all this is due to happen in 12 days' time. And if all goes according to plan, the encounter should provide important new evidence about the formation of the solar system itself. And it'll also be convincing proof, if anyone still needed it, of the ambitiousness of the Soviet space program. We'll bring you a report on what actually happens at the first opportunity. Judith.
This small silvered slide is at the heart of a new device with the potential to revolutionise medical diagnosis. It'll make it possible to test on the spot for a whole range of diseases. And it works because of the bizarre way a beam of light can be made to vanish when it hits a layer of silver. We've got a demonstration here to set it up. We've got a beam of laser light in there. Now that's directed onto this silvered slide and then reflected here. But watch that reflected beam of light when I put a drop of water onto the silver. The light has faded because the beam's energy is absorbed into the silver. Now look what happens if I drop some diluted sugar onto the water. The reflection has come back again, and this extraordinary effect can be used to detect chemicals, bacteria, and almost anything else. Now, to understand why a silver layer can be made to absorb rather than reflect light, we need to go right down to the atomic level. Without water on it, the electrons in the silver are vibrating in all sorts of directions. The photons in the beam of light are also vibrating, but totally out of step with the jumble of electrons in the silver. And it's because they're out of time that the light is reflected off the silver. But all that changes if what's on the surface of the silver changes. So if you add water molecules, for example, because the silver is only a few molecules thick, the water influences the silver electrons, which line up and vibrate in time. And if the light beam is pointed at the silver at the right angle, the photons and the electrons all end up moving in time with each other, and the light's absorbed, not reflected. So whether the light is reflected or not depends on what's on the surface of the silver. This bizarre effect has been known about since the beginning of the century, but nothing's ever been built to make practical use of it. But over here, we've got a prototype of a new blood testing kit that does, and it's set up to detect the hormone thyroxine, and we've perhaps got some, we're going to test it, in this sample of blood serum. Now, clamped under here, there's a silvered slide again, and inside the box there's a laser shining light at that, exactly like our original laser. And we'll switch this on over here, and we'll eventually get a line that shows how much light is being reflected. Now, the silver on this slide has a loosely attached layer of specially chosen antibody molecules on top of it. Now, if there is any thyroxine in the blood serum, which is now being pumped through here, it'll bind tightly to the antibody and strip it away from the surface of the silver here, changing what happens to the reflected beam of light. And let's have a look at this. Well, that's the point where the thyroxine started to be pumped through, and already you can see the change reading, quite a dramatic change. The amount of light being reflected has altered, which means there is thyroxine in this blood serum. And we can also get a reading for the slope, there it is, and a reading which shows that it's a healthy amount of thyroxine. And by putting different antibodies onto the silver, I could test just as quickly for any type of bacteria or virus. And it's so sensitive that it should be possible to detect even a single bacterium. By the end of the year, all this will be reduced to the size of a calculator. Then it may be used to give instant diagnosis in hospitals, ambulances, and maybe GP surgeries.
As you may have heard in the news over the last few days, 2 nuclear chemists claim to have made an extraordinary breakthrough in the search for practical nuclear fusion. Over the Easter weekend, scientists at the United Kingdom's Atomic Energy Authority's Harwell laboratories in Oxfordshire have been attempting to reproduce their results. They've set up a replica of the experiment in which nuclear fusion is said to occur in the laboratory at room temperature. Nuclear fusion occurs when the nuclei of forms of hydrogen called deuterium and tritium are fused together, producing energy and a neutron particle. Up to now, scientists have been attempting to produce nuclear fusion by recreating on Earth the temperatures found inside the Sun, some 10 million Celsius. But now, Professors Martin Fleischmann of Southampton University and Stan Pons of the University of Utah claim to have produced nuclear fusion in a simple electric cell. They used an electrode made out of the metal palladium that absorbs deuterium. They believe that inside the metal lattice of the electrode, the deuterium nuclei are somehow brought so closely together that they fuse, releasing energy. Earlier today, we visited the Harwell laboratory, where Professor Fleischmann came to see for himself the repeat experiment. Although this has now been underway for several days, no confirmation of the Utah result can be expected to appear for at least a few weeks.
We have spent about 5 years trying to convince ourselves that it is a load of rubbish. And we've got to the point now where we really cannot account for our results in anything but a fusion process. And this has now must be researched by other people. And they either have to convince themselves that we are right, or they have to convince us that we were wrong.
Confirmation will depend on being able to detect the gamma rays and neutrons which are characteristic of this fusion reaction. In a heavily shielded blockhouse at Harwell, 3 more electrolytic cells are being tested within one of the world's most sensitive neutron detectors. If even one single neutron were produced in here, it would establish that some fusion had taken place. Practical power production, though, would demand enormous scaling up and guaranteed high efficiency.
We have not bothered very much about efficiency. Even so, we have run some of those cells at over 100% efficiency. Now, if you project the figures which we have got to a more realistic way of doing the experiment, then our experiments indicate efficiencies of the order of 1,000%.
There's been a lot of debate over the years about whether the first organic molecules needed for life were found on Earth or arrived here on an asteroid or comet. Certainly, space debris is rich in organic molecules. Halley's Comet, for example, is believed to be about 20% organic. But it's been doubted whether these organic compounds could have survived the stress and enormous temperatures caused by hitting the Earth at thousands of kilometres an hour. Now, researchers from Cornell and Yale have used computer simulations to show how that could have been possible. This particular sequence shows a spherical comet hitting an ocean. The impact produces temperatures of thousands of degrees Celsius, shown in red and yellow. Shockwaves distort the comet into a pancake shape, and you can see material from the comet at lower temperatures in green and blue being squirted out on either side at high velocities away from the extreme heating. The organic compounds ejected in this way could, it's argued, have provided the foundations for life on Earth.
Researchers in Australia have discovered that the spiny anteater's characteristic nose enables it to sniff out more than just smells. It can also detect electricity. A team from Australia has found electroreceptors at the tip of the anteater's snout, which detect electrical stimuli at very low voltages. In tests, this has enabled an anteater to distinguish between 2 troughs of water, one with a weak electrical field and another with none. The researchers suggest that the anteater uses the receptors to search for food by picking up electrical signals given off by worms and ants. The same team discovered last year that the duck-billed platypus also has an electric nose and suggests that it might be quite common. Their next subject of investigation is going to be the mole.
As well as fusion, there's news this week about conventional nuclear power, because for the last 26 years, Berkeley Nuclear Power Station in Gloucestershire has been supplying electricity to the national grid. But in 3 days' time, it'll be shut down for good. And this will mark the start of a demolition job that will probably last 100 years. Now, there's been considerable concern about this project because nothing quite like it has ever been tried before. Berkeley is the first of 8 nuclear power stations around the country which will be shut down over the next 10 years. So therefore, it'll represent how the Central Electricity Generating Board intends to tackle the problem. Well, first, the highly radioactive fuel rods from the core here will be taken out, and then most of the rest of the power station will be cut up and carted away. But one important part of the site will remain untouched. And this is it, the reactor vessel which contained those rods and its surroundings, which over the years of operation have become too radioactive to handle. The CEGB has decided to leave this part for 100 years, not only to let it cool off, but also to let the demolition technology that will take it apart improve. Now, when Berkeley was first built, little thought was given to dismantling its radioactive core. Access to this area, even for robotic demolition vehicles, will be very difficult. So the CEGB has put aside money, around £40 million. In 100 years' time, interest should have bumped the sum up to around £250 million by today's prices, enough, they hope, to cover the cost of demolition. Some critics believe the CEGB have underestimated this cost, and with privatisation on the way, the guarantee that these costs are covered is essential.
There's also been criticism of building reactors that are so difficult to take apart. The CEGB is now constructing a whole new series of nuclear power stations with pressurised water reactors. The first is at Sizewell in Suffolk. But will they be any easier to take apart? Well, the public inquiry before building at Sizewell began concluded, amongst other things, that it was most important that decommissioning should be made easier wherever possible by design measures. Sizewell will certainly produce less radioactive waste. For a start, the reactor vessel, just there, is far smaller than at Berkeley, and the steel used contains less impurities and so will pick up less radioactivity. But decommissioning will still take 100 years. There are further design measures that could be taken to ease demolition, but this is where the economics of 100 years works against the CUGB. If they spend an extra $1 million now, during construction, it will have to save them at least 10 times that in demolition costs to make it worthwhile. The view in the nuclear industry is that some of these design measures are simply not worth taking. It's better to leave future generations the money to cope with the problem.
But there is another option. Leave the old reactors exactly where they are and then entomb them in concrete forever. After all, they only take up about 5% of the site and the rest of the site could be reused. Many environmental groups favour this option because they prefer it to breaking open the old radioactive cores and transporting them across the country to a waste dump. For the moment, the CEGB remains committed to its 100-year plan to totally dismantle these stations. However, after privatisation, their successors may think differently. After all, a century is a long time in the nuclear power industry. Well, now a report from Maggie.
Winchester, noted for its cathedral, and a few hundred yards away, the scientific centre of a computer multinational, where they've been developing new ways of looking into the past. For example, to the left of the cathedral, there's not much to see today, but it's the site of a very much earlier structure. Let's take a look inside. Long since gone, the ancient Winchester Minster. Impressive. But how much of this is guesswork? Well, they're not too sure about the structure of the roof, how many beams there would have been, for example. But the archaeologists who worked on this are fairly confident about the rest. On Tomorrow's World, we've already seen one example of what computer programs like this can do. At Sutton Hoo, this was a reconstruction of a body buried near the Longship and its famous treasures. So you can build on sparse archaeological data. This is a gravesite on the Isle of Man. There's not much to show for it today. But this is probably what it did look like, according to Paul Riley, who's done much of the work on these programmes. Now, after he'd done all this work, he discovered that the site had indeed been dug back in 1917, and the results of that dig are consistent with this picture. So it seems as if the computer is now ready for use as a practical archaeological tool. And here's their next site, set in a Welsh valley and associated with the Princes of Powys. This is Mathravel. Thought to date back to the Dark Ages, you can see long ditches around the outside and a mound at the back. But there's a flattish bit in the middle. Is that of any interest, Paul?
Actually, that's the most exciting part of the site as an archaeologist, because that's where people would have lived. Now, we'd dearly love to know more about what these people were doing, but rather than going straight into excavation, we'll apply other techniques to bring out as much information about the site without ever doing any harm. One method is to survey the surface, produce a topographic model. Now, to do this, we take laser theodolites with small computers, and we take many thousands of readings from all over the site and model the surface on a computer. But we've enhanced the features so that the moat, for instance, is slightly bigger and the ditches are much deeper. But what has happened is we've managed to bring out some of these smaller features. You see there's these linear platforms and so on, and these hollows. Now these will probably reflect small features which we couldn't really see very clearly on the surface. House platforms, maybe perimeters of other buried features. What we really need to find out more about the site is what's going on below the surface. Now, we put probes into the ground, we pass electricity between the probes and measure the resistance. It's actually measuring the humidity in the soil, and certain features, for instance, walls or ditches, will register differently. And again, this data can be presented on the computer and enhanced to bring out particular shapes which we can try to interpret. For instance, you can see here, there's an area of high readings around the edge and across it. Now, these high readings maybe represents a wall or a stone foundation, for instance.
And what's next?
Well, another technique we can apply is to use the proton magnetometer. Now, this works something like a very powerful metal detector, but in this case we're measuring tiny variations in the Earth's magnetic field. Features like fireplaces where the clay's been burnt leave fossilized magnetic imprints on the ground, and we can measure these and we can present this as a graphical form. We've got low values in the blue range going up to high values in the red range. And we've got some very interesting anomalies here. We've got this nice green feature here, which to my mind looks like the traces of burning, perhaps a palisade. We've also got these two very strong red. Now, they're very high readings, and they're probably burning for some kind of kiln, for instance. This one's most interesting, nice strong red readings, but in the middle we've got low green, which suggests it's a square shape which is burnt down, perhaps a building.
And here's a first guess at a computer reconstruction of those features. But not only that, Paul can now produce a potted history of the site, from the earliest rectangular enclosure with a straight fence and deep ditches, which in time began to erode away. But then, in a new phase of building, the kilns appeared. And also, that large rectangular structure, perhaps associated with another building on the mound. And of course, the wooden palisade. So did it really look like that? The archaeologists plan to dig at Mathravel later in the year. And now they'll be able to plan exactly where to dig, so that they learn most from the least effort, and also by doing the least damage to an attractive site.
Well, this isn't quite the normal sort of table you'd expect to be playing table tennis on, but then again, it's been designed so that robots can play against each other. And my opponent tonight in our continuing quest for the ultimate ping-pong player over there is Charlie. Now, Charlie will be competing next week at the Edinburgh Science Festival as the UK representative, and he'll be playing opponents from Sweden and Finland. He's not in his best form tonight, but we're told that he's going to be absolutely up and running next week. Now, the idea behind the competition is to design more agile machines that could later be used in industry. And, well, I'll tell you that Charlie can, when he gets going, do this in milliseconds. He's only got milliseconds to work out where the ball's coming from, the height of it, and also when to hit the ball back. And the whole thing works from photosensitive cells and mirrors. And if I bring this ball across here, he might react to this. He sometimes does. He's been snapping at me all day. I don't think he's going to do anything. No, he's not. All right, well, what happens anyway is the ball comes across the table, and 16 photosensitive cells there. One of those photosensitive cells is triggered, and that tells the robot the line of the trajectory. Now, the same photosensitive cells, along with the mirrors here, tell Charlie the height of the ball and when to raise the bat to hit it. And we'll have to wish him luck, I think, for next week, because he's certainly not going to perform for us tonight, although he's been doing really well all day. Never mind, it just means that I don't have to make a Charlie of myself playing him. That's all we have time for tonight. Thanks for watching. We'll be back at the same time next week. Till then, good night.